Hello, everyone. I'm Zachary. I'm a PhD student at Columbia University. Today, I'm super excited to share our latest project, DreamBoost, train trees on databases with only SQL queries. This is a joint work between Columbia University and Microsoft. So we all know that machine learning on databases is popular these days. Major databases providers like Azure, Google Cloud, and AWS have been offering machine learning support for a long time, and it's proven to be very, very effective. These models, like tree models, are dominant for tabular data sets common in databases, as shown by the Kaggle survey last year. Among all those popular machine learning algorithms, decision trees, modern forest, and gradient boosting take the lead. So in response, machine learning communities have developed machine learning libraries like LightGBM and XGBoost that offers user-friendly API and superior single-node performance. Now, you may think that applying tree models to databases is natural and easy. Databases are full of tabular datasets, and tree models are specifically designed for them. However, the process may not be that simple, as illustrated next. So let me illustrate the challenge with an example. Imagine you are the owner of a global bakery chain, and you have been collecting customer ratings from platforms like Yelp and Google. These ratings, like the one to the right, are precious data for your businesses, but now you want to use them to predict your future customer ratings. So ideally, to build machine learning models for this rating prediction, you want to go to your databases, specifying the rating as your target variable y, and pick features such as the K price, customer age group, weather, and the location as x. Then you feed this table into the machine learning libraries and hope that it magically return an impressive model to predict the future ratings. However, the process is not as easy as it sounds. The code challenge lies in the impedance between how databases and machine learning libraries handle datasets. So database stores data across various tables. For a bakery chain, the ratings are in the middle table, but other features like customer ages, and the store locations are scattered across different tables. However, machine learning libraries requires a single table with both feature x and target variable y as inputs. So this creates a gap between how databases and machine learning libraries structure datasets. The current solution to bridge this gap is to use a SQL query to join these tables together, materialize the results, and export the result to the machine learning libraries. However, such a join, materialization, and export processes causes lots of troubles. Well, firstly, the process is very laborious. Ideally, we would just want to select features we need for machine learning from the databases. In reality, however, we need to navigate through a complex schema to write SQLs. And the structure of enterprise database schema can be very complex. Take a look at the IMDb schema displayed below, which we refer to as a galaxy schema, because tables are scattered around just like stars in the galaxy. And imagine having to navigate through this strong graph, write this long SQL, and ensure its correctness. It's quite a tedious task. Secondly, it's very slow. Ideally, the majority of our time should be invested in improving machine learning models. But in reality, the join, materialization, and export process, especially for most of our datasets, can take hours to complete. So our experiments actually show that such a join process in databases can take longer than the actual training time. Lastly, there is a security risk. As we transfer the raw data from the database to machine learning libraries, we expose ourselves to potential data breaches. Imagine if data contains sensitive customer information like social security numbers, right? The resulting legal issue could be a nightmare. So in short, previous machine learning libraries require moving data from databases and use specialized machine learning system to train models. This comes with a set of challenges, but what if we could reverse this process? What if we could train models using only SQL queries and bring machine learning back to data? So we introduced DreamBoost, train tree models purely with SQL queries. DreamBoost is an open source project, and you can scan the QR code on top right to check out our GitHub repository and a code demo. So instead of moving data to machine learning, DroneBoost translates machine learning as SQL queries and moves SQL to databases. As a result, the training process is simplified down to executing SQL queries, and it all happens within the databases. Once the training is complete, the model parameters are returned as SQL query results. Note that your data never leaves your data set. Your data never leaves the database. It provides a strong data governance. So what exactly is DroneBoost? DroneBoost is a lightweight Python library that is as easy to import as XGBoost and LightGBM with similar training APIs. But instead of running training locally or on specialized machines, DroneBoost plugs directly into a database. Below is the code snip of how to use DroneBoost, and I will walk through it line by line. Firstly, you need to connect to your databases. And DroneBoost is highly portable. It can connect to any SQL running databases. This includes single node databases like DuckDB or Postgres, and even cloud databases like Azure, Redshift, and BigQuery. Beyond that, it can connect to data frames like Pandas, R, cuDF, or Dask. Next, we map out the drone graph. So unlike XGBoost and LightGBM, which only work with a single table, DroneBoost is designed to manage many tables as a drone graph. So in our example, we lay out the drone graph with two nodes, sales and date, each representing a table. We specify a rating as target variable y, and weather is the feature x, and we link these two nodes with an edge for the drone key. So here they're drawn based on the data ID. Notice that in the most of the case, DroneBoost can infer the drone graph automatically based on your primary key and foreign key constraints inside of the databases, and only require user input for ambiguities. Finally, we move on to the model training phase. DroneBoost trains machine learning algorithms using pure SQL queries and executes them within the databases. It employs various optimizations, and the crux of this is a technique called factorized learning, which trains models over the join, but without actually materializing the join, which avoids these high overheads and greatly accelerates the performance. You can find more details in our technical reports. So how fast is DroneBoost? When data fits in memory, DroneBoost is 3 times faster than specialized machine learning systems. We ran experiments with training random forests with 100 trees. On the graph, the x-axis shows the number of trees, and the y-axis shows the training time. Starting with scikit-learn, a popular choice, but it's quite slow, so we have to stop it after only training 30 trees. Next up, XGBoost and LightGBM. They are faster, but they start with a high intercept on the y-axis. The high intercept is due to the costly process of join and materialization, which we illustrate here with the black dotted line. Finally, we get to DroneBoost. It's 3 times faster than specialized machine learning system, even when running on DuckDB, a general purpose database systems. Right, this is because DroneBoost avoids the materialization overhead, and it even finishes the training between the join materialization finishes. Finally, what if data doesn't fit in memory? Specialized machine learning libraries like LightGBM and XGBoost can use Dask for distributed learnings. So we compare them with DroneBoost using Dask SQL. The task is a gradient boosting for on 4 virtual machines, each with over 100 GB RAM. We plot the training time against varying database sizes to the right. When database size is 40 GB, DroneBoost is 9 times faster than XGBoost. But in contrast, LightGBM hits out-of-memory errors even on 4 virtual machines and is therefore not plotted. Pushing the envelope further, we increase the database size from 40 GB to 1 TB. For LightGBM, this task will be daunting as it will theoretically require setting up and manage over 100 virtual machines. But for DroneBoost, it can translate training into SQL queries and naturally piggybacks on cloud databases to do the training very scalably. So the graph to the right demonstrates how the training time of DroneBoost naturally decreases with an increased number of nodes in the cloud databases. That's it. Thank you for listening. Remember, you can always play with DroneBoost yourself, scan QR codes to try out our demo on Google Colab, which even works on mobile. Thank you so much, and happy to take any question.